Capacitors are rated by their ability to store a charge, and by the maximum voltage with which they can be used. Capacitance is measured using the farad F. The capacitance of a capacitor depends on several criteria. The surface area of its plates. The distance between the plates, or rather, the thickness of the dielectric. The type of dielectric. A capacitor that has large plates close together will have a higher capacitance than a capacitor with the same dielectric, but with smaller plates or plates that are farther apart. In a DC circuit, after the capacitor becomes fully charged, it acts as an open circuit and current stops flowing in the branch of the circuit that contains the capacitor. In an AC circuit, capacitors also offer opposition, called capacitive reactance, but do not act as an open circuit when an AC voltage is applied. Switches. A switch is a simple device for opening and closing an electric circuit. When you turn on a light switch, for example, the switch and the circuit is closed. This means that the switch completes a conducting path, and the current flows from the voltage source to the lamp, then back to the source. Figure 6.18 shows the schematic symbols for switches. These are the most common types of switches. Single pole, single throw, SPST has only two positions, open or closed, and can open or close only one wire in a circuit, such as a light switch for a single lamp. Double pole, single throw, DPST has two separate sets of contacts, and can open or close two circuits at a time. It also has only two positions, open and closed, as in a light switch for more than one light circuit. Single pole, double throw, SPDT has two positions, closed and closed. In essence, it is a toggle switch that enables you to switch between two different circuits. Throwing the switch to one side closes one circuit and opens an adjacent circuit. Throwing it to the other side does the reverse. Some SPDT switches have a middle position that leaves both circuits open. Double pole, double throw, DPDT can make and break contact between two wires at a time. It has 6 terminals and can have either 2 or 3 positions. If there is a center-off position, both circuits are open. SPS Magnets and electromagnets. Two main types of magnets exist, natural magnets and electromagnets. Natural magnets are materials that attract pieces of iron, and can be either temporary or permanent magnets. Electromagnets are artificial magnets, made by passing electricity through a coil of wire wound around an iron core, or by inserting a magnetic material into the magnetic circuit of a solenoid. Electromagnetism is the magnetic effect produced when electric current flows through a conductor. Our discussion focuses on electromagnets, which are an integral part of an electrical circuit. If a piece of magnetic material is anywhere near a magnet, the magnet will affect it. How the material is affected depends on its placement in regard to the magnet. The area around a magnet within which it can produce a magnetic effect is the magnet's field. You can indicate the shape and strength of a magnet's field by using lines, called magnetic lines of force. Notice that the lines of force are closed loops. Every line of force leaves the north pole of a magnet, makes a complete path through the surrounding space, or material, and returns to the south pole. The lines run from the north pole to the south pole outside the magnet. They run from south to north inside the magnet. Figure 6.19 shows the magnetic fields of a bar magnet. NS. You need to know several terms describing magnets and magnetic materials. Permeability is the ease with which a substance passes magnetic lines. Reluctance is the opposite of permeability, and is the opposition that a substance offers to magnetic lines. Retentivity, or residual magnetism, measures the degree to which a substance remains magnetized after the magnetizing force is removed. Magnetic flux is the quantity of magnetism, expressed by the total number of magnetic lines of force that passes along the magnetic circuit. Flux density is a measure of the magnet's strength. measured along the number of lines of force in a unit of area, usually 1 square centimeter. If you place a small compass near a wire through which a current is flowing, the compass needle will move to indicate the presence of a magnetic field around the wire. The field is circular, and its direction depends on the direction of the current. If a conductor moves through a magnetic field, the field will induce a voltage in it to create magnetic induction. For electromagnetic induction to take place, there must be a magnetic field, conductor voltage, and relative movement of the field and the conductor. Using the left-hand rule. Just as a permanent magnet has a north and south pole, so does an electromagnet. Both the direction of the current and the way the coil is wound affect the coil's polarity. To determine which end of a coil is the electromagnet's north pole and, by extension, direction of current flow, use the illustration in figure 6.20 and the left-hand rule, LHR, which is as follows. 1. The current leaves the negative terminal of the battery and enters the left end of the coil. Pretend to place your left hand at the left end of the coil. 2. The wire in this coil goes over the core at the point where current enters the coil. Curl the fingers of your left hand, theoretically, around the coil in the same way the wire winds around the coil. 3. The thumb of your left hand now points in the same direction as the north pole. Because your thumb is pointing to the right end of the coil is the north pole. Core. Figure 6.20 using the left-hand rule. Using the right-hand rule. By using the right-hand rule, RHR, you can determine the direction of the magnetic field in the area around a current-carrying conductor. The RHR states that if you, theoretically, grasp the current-carrying wire with your right hand in such a way that your thumb points in the direction in which the conventional current is flowing, your fingers will point in the direction of the lines of force, or the magnetic field. Encircling the wire. Use the left-hand rule, LHR, to determine magnetic poles, and use the right-hand rule, RHR, to determine the direction of the magnetic field.